So I think you summarized pretty well my field and what I'm interested in, and more broadly in our group we're interested in far from equilibrium material behavior, and more particularly dynamic conditions, and even more specifically impact loading conditions. So this work was done in collaboration between two groups, mainly between the Chris-Nelson group and Christopher Shu group at MIT, and with my good colleague Mostafa Hassani, who is not at Cornell University, and Yu Chen San, who is a graduate student at MIT. So today what I'm going to talk about, it will be more particularly about micro-impact loading conditions. And but first, just to tell you why we are interested in we're interested in them for multiple reasons, and we are studying microparticle impacts for a lot of applications. The first one that can come to mind is for protection against hypervelocity impacts from debris around the Earth, also space dust. So here it's actually a short video showing, if it can load, showing all the tracked objects that are around the Earth, and these are large objects, but also micro objects can travel at high velocity and can cause large damage in spacecraft and also in personnel. There's also outside of the direct proximity of Earth, there's also dust. Scientists are interested in collecting the solar system dust to study the origin of the solar system. Now, in our group, we're also interested in more down-to-earth applications, in particular the cold spray from the cold spray industry. So the cold spray, it's an additive manufacturing method that is based on impact bonding and repeated impact bonding of microparticles or metallic powder. And I was also interested in microparticle erosion and how microparticle erosion can damage structural materials or such as eroding rotor blades or inner walls in pipelines carrying oil. Also, they can present a threat to gas turbine engine. So today I'm going to focus particularly on these two phenomena. So impact-based bonding and microparticle erosion. There's also application for inertial confinement fusion experiments, laser-based ones, where there's a lot of ejecta that are created during these experiments, and these ejecta traveling at high velocity can impact and damage equipment and reduce the efficiency of the apparatus. And there's also another avenue in my research where we're interested in impacts in soft materials and soft tissues, where these microparticle impacts, these microparticles can get embedded in tissues and also lead to long-term issues. And they can, on the other hand, be used. This microparticle can be used to carry drugs and for targeted drug delivery or needleless drug delivery. So the challenge so far is that in the experiments that are done in the laboratory is that most of the study they've been relying on multiple particle experiments, where it's difficult to distinguish between each singular impact events, and also the characterization have been focused on post-mortem analysis. But to make an ideal experiment would actually be looking at single impact events, so with a single impact, and look at what happens in real time, where there's more information to be learned in real time, and then you can always do the post-mortem analysis. So this is a famous example of a single impact experiment done by Edgerton at MIT, where you can see the impact events in real time, which is more instructive than just looking at the outcome. So the challenge in microparticle high velocity impact is that we're dealing with particle sizes that are of the order of 10 microns, with impact velocity up to a kilometer per second or a few kilometers per second. So the characteristic time of an impact event is about 100 nanoseconds. So to be able to look in real time at such short time scale, you need high frame rate imaging capabilities. So of the order of 100 million frames per second, which is quite high for conventional, or it's too high for conventional cameras. So you need more specialized imaging techniques. So this is just the outline of the talk. I'm going to present first our experimental the platform that we developed at MIT, which is what we call it the laser-induced particle impact test. So, and then I'm going to show you how we used it to study impact behavior of metals. So let's start with the experimental method. So I was saying that it's an all-optical method for micro-impact experiments. So we use to look at real-time the impact. We use a microscope, so a high-speed microscope, where we position the microscope objective to look at the impact site. Now we use a laser pulse to generate a plasma. This plasma is absorbed in this thin metallic layer. The laser is absorbed in this thin metallic layer. Upon laser absorption and ablation, you generate a plasma, and the plasma would quickly expand and push this elastomer layer, on top of which we deposit micro. As this polymer layer deforms upon plasma expansion, it pushes the particle into air or vacuum, and then we position a target in front of it, and we can look at the impact as it happens. So using this method, we can by changing the laser energy, we can vary the particle speed from tens of meters per second up to a few kilometers per second, and because it's optical, everything is optically controlled. We have high repeatability, high reliability of the impact events. So we know with a good precision, with a nanosecond time precision, the impact instant. So we can trigger the camera and look at the right timing. We can also adjust the angle of impacts, even though to them I'm only going to show normal impact experiments. And there's no limitation on the type of particles that we put on this assembly. So we've done many experiments with ceramics particles, silica, alumina, so hard particles, and then a lot of different metals, and also polymer spheres or polymer particles. So this technique allows us to do microscale assessment or microscale study of deformation of targets and particles, and failure at really high strain rates. So the strain rate that here we're talking about is 10 to the 6 or 10 to the 9 per second. So this can be related to the previous presentation by Jen, where we can use this apparatus to do high strain rate testing of materials and look at the impact resistance of the materials under impact. Let me show you just a video of an aluminum particle on aluminum. The impact occurs at about 600 meters per second. So if I play the video, you see the particle approaches the surface, deforms upon contact with the substrate, and then rebounds. So you can see this video is made of 16 different frames. This is because the camera is limited by 16 frames. That's how you can get 300 million, up to 300 million frames per second. Now let me show you how we use this experimental platform to study the dynamic behavior of metals. So first, what happens when you launch a microparticle toward the metallic target? So we know that at very low velocity, the particle is just going to rebound, and this is Hertz and contacts, pretty well known. And then here, let me show you an example where the rebound velocity is close to the velocity. So this is a zinc-based bulk metallic glass. The particle comes from the top, impacts the target, and then rebounds at a velocity that's close to the impact velocity. So we can consider this impact to be almost purely elastic. So there's no energy loss. Now, as we increase the impact velocity, we enter the bonding regime, and this bonding regime has been demonstrated in the industry, and that's at the basis of the cold spray method. So in the cold spray method, you repeat these bonding events, so that after a repetition of these impacts, you can build coatings, or you can manufacture 3D pieces. And so this has been shown at the multiple particle level, and we confirm that we can observe a single event in this process. And here's an example of what we get when we have an aluminum particle impacting an aluminum substrate. So where the impact velocity is 800 meters per second and the rebound velocity is 0 because the particle sticks to the surface. Here I'm showing it again. Now, with there's a question in this field is about the transition from this rebound regime to the bonding regime, and the question has been: is this transition gradual, or is it a sharp transition, or is there a critical, well-defined threshold velocity or critical velocity? And the challenge is so far is that there hadn't been any direct measurements of this critical velocity because of the lack of experimental method, and more critical velocity estimations were based on simulations and indirect measurements and statistical analysis on multiple particle experiments. So because of the lack of direct measurements of this critical velocity, there hasn't been a consensus on the bonding mechanism. So what causes the particle to stick and not keep on rebounding? So a lot different hypotheses have been put forth, including adiabatic shear localization, mechanical interlocking, or localized melting, or a combination of those to explain bonding. So this is the problem that we decided to tackle. So to do so, first we aim to identify this threshold velocity. So here I'm putting on the right what we call the coefficient of restitution, which is the ratio between the rebound velocity and the impact velocity as a function of impact velocity. So when the particle rebounds, then this ratio is non-zero, and as the particle bounds, this ratio drops to 0. So as we increase the velocity, we can see that there's a trend toward lower and lower coefficient of restitution. So and we approach the zero value. So this is just, again, these experiments, and then we see that as we keep increasing, then there's a sharp threshold between which the particle rebounds or bound, and this is what we identify as the critical velocity. Now we wonder what happens exactly in this interframe when the particle is still in air and when the particle has bounded, because we really want to know with the precision as high as possible what exactly happens. So here is a zoomed in time phase, so with shorter interframe time into what happens. So if we look closely, here the particle deforms quite largely actually, but still rebounds, and it gets this oblate shape. Now, as the particle is above this critical velocity, the particle deforms, but there is also this large jet forming at the periphery of the particle, and this large jet is what we attribute to the origin of bonding. So when this jet forms, there's a large plastic strain at the interface between the substrate and the particle, and this large sudden strain and jet cleans the surfaces, so cleans the surfaces from oxide layers, and brings into close contact pure which leads to bonding. And there's also an additional energy dissipation mechanism associated with this jet formation that is not available for rebound. So this jet formation is something that's known in different contexts, in liquid impacts or in shape charge experiments, and it originates from the shock wave interaction with the particle surfaces on the particle edge. So as the shock develops and propagates into the particle, it detaches from the edge, and then upon detachment, there's a release wave that leads to this jet formation and this spall phenomena. So I'm going to save you from the formula, but based on this picture, we aim to identify the critical velocity at which this jetting phenomena. So we derive these simple formulas, and then with further simplification, we arrive at this ratio. And this critical velocity over the bulk speed of sound in metals is about a constant for pure metals. So we can be approximated as a constant for pure metals, which would lead to a critical velocity that's proportional to the speed of sound. And this is what we verify experimentally for a variety of metals, zinc, copper, etc., for matching materials. So where the particle is the same as the substrate material, and for normal impacts. So now we can. So now that we have identified the origin of this transition between rebound and bonding, we decided to go even higher in impact velocity and to look at another extreme phenomenon, which is the erosion regime. So it's that as when you enter like the hypervelocity regime, or when you keep increasing the impact velocity, you start degrading the target. So you start to have a loss of material on the target. So this is something we decided to look at. Again, increasing gradually the impact velocity from low velocity regime where the particle rebounds to the bonding regime where the particle sticks to the surface. So this is for tin on tin. So the particle remains on the surface, and then as we keep increasing, we see this particle now rather than bonding fragments, and there's this large splash that is created at impact. If you keep increasing even further up to 1100 meters per second, you see that it's hard. You can hardly distinguish the fragments, and the impact resembles liquid. So our question was, do we actually melt the material, and is because once the substrate is melted, then there's very low strength between the melt and the solid, and then this melt can just be lost. So to check, we looked at post-mortem observations. So we have a small indent at low velocity to bonding, where the particle sticks to the surface, and then as you keep increasing the velocity, you see this particle lost its shape, but also fragmented, and you can observe the emergence of melting that you can see in these round features. So surface tension dominated shapes, and then as you go even higher in velocity, you see that this crater like a full melted and re-solidified crater. So we can verify using confocal microscopy that there is actually overall loss of material, because you have more volume that is lost than what would be gained. So in this melt-driven erosion regime, we can also derive using simple equations to estimate the threshold for erosion. So I'm going to save you from the equations, but they can be found in our papers. So we can predict this erosion velocity based on thermal properties from the substrate and particle, and also the density of the particle and the diameter of the particle. So it's a size-dependent velocity. And then we verify our estimations or prediction for with good, with relatively good agreements for matching materials, but also for unmatched materials. And I also want to point out to the fact that we can, because the bonding and the erosion mechanisms are based on different physics. So one being the pressure-driven jet formation, and the other one being melt-driven erosion. You can go from the rebound regime directly into the erosion regime without going through this bonding regime. So this is the case where we observe in like on bismuth, where the bismuth never bonds to the surface because erosion occurs first. And then just in a couple more minutes, I will show you more of our ongoing work and just work that we are initiating and we are recently published. Is that now we are also interested so the particle and the substrate are made of different materials, and we see three types of regime. So penetration, which is, for instance, copper and aluminum. The copper particle penetrates deep in the aluminum without really deforming. Then we have a co-deformation regime where the particle deforms or is strained to the same amount, relatively same amount as the substrate, which is the case for copper and titanium. And then at the other extremum, you have splatting, where the particle largely deforms and the substrate is barely deformed. And we are we came up with a predictive indicator that's based on the density of the different materials and their yield strength, and again with the speed of sound of these different materials, because it's a shock related phenomena, and where this the different regimes that we observe. And with this, I just want to summarize that that's about the different phenomena that we've been looking at. So rebound to bonding and bonding to erosion transitions, and we are like now looking further into these similar materials. And thank you for your attention. And please ask any questions. And also you can shoot me emails with questions if we don't have time to answer them all.
Thank you, David.
Thank you.
Thank you, David. It's very interesting and fundamental work. Let's, due to the interest of time, let's give 2 to 3 questions. And this is the first one is Chen Xi, and propose promoting to analyst. So let me first ask a question. So when he joined the panelists, he may further actually formulate a question. His question is, he actually asked 3 questions. The first question is, the particle is solid or liquid? The second one is, do you have any idea if substrate is a metal poor or not? The third question is, what is the specification of the camera? So I will propose Chen Xi to the panelists, and in this time, David, you may just comment on these 3 questions.
So your first question was whether or not the particle is melted.
So is it solid or liquid? He is asking.
The particle, no, the particle is solid. So when we shoot the particle is solid. And then this is ensured by the fact that the particle, even though the launch is quite a solid, and it's like plasma based, so there's the plasma, there's a good, we have a thermal barrier that's provided by this polymer film, and the particles also travels relatively long distance before reaching the target, and the distance during which, based on our estimations, the particle cools down to room temperature. So the particle is solid and is at room temperature before the impact.
Yeah, I noticed you has been promoted. You can just comment if you have any other questions. Yeah, David, go ahead.
And I forget your second question. What was your second question?
The second question is, do you have any idea if substrate is metal poor?
If the substrate is?
And Chen Xi, are you online?
Oh, yes. Thank you,
yeah.
David. Yeah, so my question is, if your substrate is beautiful, means your substrate is liquid.
So this
because now you spread your solid particle into a solid substrate, right?
Yeah, that's right. That's right.
Because most process for AM or additive manufacturing, so actually they have to generate a mute pool on the substrate, then spread the solid particle into the mute pool, right?
Yeah, so that's right. So that
So that's asking, do you have any opinion about
so
this?
that's the advantage, and that's what people doing cross-spray actually to promote their method, because under the right conditions, the bonding happens at the solid state. So you don't have any melt happening. So this is why you can keep good mechanical properties without going, and you're not going through melting and what is associated with melting. Now we also in different work we've shown that for some particle combinations and some velocities you can and as I showed for erosion, you can create a melt zone at the interface between the particle and the substrate. And actually this melt is detrimental because it would prevent bonding between the particle and the substrate. And this melt actually acts more like a just instead of bonding, it just rebounds and slides away. So melting is something that's people in the industry, when they want to do additive manufacturing using this method, try to avoid. But that's a big question in the field too. That has been a big question in the field. So yeah.
So yeah, thanks. So I have a further question. So because for your camera, I'm wondering how good your camera is. Is there any special specification for the camera?
So this camera is different from a conventional camera because so it can reach to really high, so to nanosecond interframe time, and the way it does that is by having multiple detectors. So you have, it's quite a large camera. I can give you the specifications, but it's a 16 cameras, and you can trigger each camera individually. So actually that's why you have such short sequences, because it's only 16 images that are stitched together to make a video. And this camera, and so the exposure of this camera is, so it's in intensified CCDs, and the intensification can be made on nanosecond timescale. So it's a specialized imaging. They do this in this sort of high-speed camera, and they're quite expensive too.
Okay, thanks.
Thank you.
Thank David, and thank Chenxi. If there's no questions, let's thank David again. Then we can move to the last speakers.